let's talk about that a little bit. So normally people who speak are introduced and then they start out by saying, they thank the organizers for the opportunity to speak. And when there is degeneracy like this, it gets a little awkward. But I had one occasion where the degeneracy was lifted in an interesting way, where in some meeting that I organized, one of the American colleagues couldn't make it because he didn't realize he needed a visa or something like that. In any case, he didn't get the visa in time to come. So in the last minute, I had to replace him as a speaker. So I started out saying, I would like to thank one of the invited speakers for this opportunity to talk. So anyway, today is not so bad. It's okay. So what I want to tell you about is probably familiar to a good many people here, but some work we've been doing trying to understand yielding in amorphous solids, and it touches upon a lot of different aspects of the program that we've talked, we've had in the last few weeks, and for reasons of coherence, so to speak, I will focus on one element, which is the yielding transition. But I will mention a few other things as I go along to indicate the other connections, okay? So this is sort of the outline of my talk. I have a lot of generic introductory material, which you probably don't need. So what I'll plan on doing is to go through them fast, and if you need me to, you stop me and I can say more, okay? So I'll say a little bit about mechanical response of amorphous solids. I'll tell you about the particular thing that we've been doing, which is to probe the mechanical behavior through oscillatory shear deformation of a model glass in this case, but we are also looking at other systems. And under such deformation, what one sees in the first instance is a non-equilibrium transition in a driven system, because that's what we have. We're driving this amorphous solid, and we see a non-equilibrium transition where characteristics change. What we have then done is to sort of identify this non-equilibrium transition as the yielding transition that people study. In discussing the yielding transition, there are sort of various pet notions that people worry about, which are relevant in some contexts and may or may not be in this context, such as avalanches, and I'll tell you what they are. And this is something that we looked at in some detail to understand what the avalanching behavior in glasses was under cyclic loading. There are some surprises, and the other side of the coin is, this is now with avalanches, the surprise was what happens below the yielding transition, and the quick summary, which was sort of contrary to what was expected, is that you don't really have anything interesting happening, and the yielding happens as a discontinuous transition. And on the other side of the yielding transition, you have something else which we were not particularly looking for, but has become interesting to try and understand, which is the formation of shear bands, okay? And so that's what I will spend some time talking about, okay? And along the way, I will mention, like I said, a few other dimensions of what may be interesting. And this is a work that sort of started a few years ago in collaboration with this student, Davide Fiocco, and Giuseppe Fofi, who was here in some parts of the program, who was then a faculty member at Lausanne, and currently is at Orsay. And in the recent times, these are the two people who really sort of did a lot of work Prem Kumar Leshantam, and Anshul in particular, is now not here anymore. He's left for a postdoc in Montpellier. And Saurabh Kumar was a bright young undergraduate who came and spent a couple of summers. And I don't know if you recognize the place. So he's actually doing work for me, not in the field of science, but
he's doing work in the field.
In the field. So that's the only picture I have of him for some reason. So, okay, so all right. Now this is I won't dwell on this, but people have worried for a long time about how to characterize mechanical behavior of solids, and this is sort of a textbook cartoon set which introduces various concepts. This is the thing that we're going to be worrying about, right? Which is if I apply some kind of stress or elongation in this illustration, up to some point I can imagine that I have elastic response. But beyond a point that becomes untenable, I begin to see indications of irreversibility. And the point, if there is a point at which it happens, at which irreversibility sets in, is what you would like to identify as the yield stress or strain, depending on which protocol you happen to be using. And understanding the onset of irreversibility in the mechanical deformation behavior of solids is obviously important in general, and it's a very widely studied field of engineering. But the particular subset that we're going to be focusing on is looking at glasses. And this too is a widely studied problem of applied interest. But we are going to be focused on trying to develop a microscopic description and an understanding of what really happens when you hit the yielding transition, right? This is more sort of illustrative material to say, as a material scientist, you really do worry about what is a reliable range over which you can expect sort of reversible behavior, response of a material, and how high in stress you can go being in this elastic regime is really important. And it turns out that for amorphous solids of a certain kind called metallic glasses, that limit is very, very high, okay? But something as a materials property you also worry about is that if you do hit some kind of limit of elastic behavior, you don't want dramatic things to happen, right? So if you're taking a steel rod and you're applying tension, applying stress, you want it always, or not always, but a lot of the times you want it just to come back. But if you do apply enough stress that it doesn't come all the way back, you want the incremental, or rather, you want the plasticity that it develops to be incremental, right? So you want sort of ductile behavior, in other words, as a desirable property. You don't want ductility at small stresses, you want it at the limit of stability, right? But, you can't have everything. So with amorphous solids, what seems to happen is that you have a fairly large elastic regime, but when it fails in a very brittle fashion, right? And so you have the formation of these entities which are called shear bands. And so one of the goals is to sort of understand how and why for these materials these shear bands form, and is there something you can do about preventing them, right? But the news on that is probably not good. We'll see at the end of the talk. Now, this is, of course, a very material sciencey motivation for looking at this problem. But if you just think for a minute, the plasticity and flow of amorphous solids is actually a very widespread phenomenon, right? So you have it okay, the first example is the least obvious, but it's there for a reason. This kind of behavior is seen in disordered matter in general, and one popularly studied example is magnets with disorder. And so then you have problems like the movement of a fluid front in a disordered medium, and you have granular matter, and geophysically you have things like landslides and real avalanches. Not, I mean, this is where the word comes from, when you have small perturbations leading to large-scale motion of snow, and earthquakes. These are all examples of something drastic happening in amorphous matter under sufficiently large external force. Okay, so whatever one can come up with in understanding amorphous solids has wide-ranging implications. I didn't even mention here, in fact, a closer home domain of soft solids, which is again a big world, and partly I don't mention it because I sort of, when I talk about amorphous solids that we study, I have those in mind, but they come in a wide range of characteristics. You have things which are very, very soft. In soft matter, this is, so people don't treat even, in terminology, they don't even treat them as legitimate solids. They're called yield stress fluids, right? So that's one end. And something like the amorphous solids that I described is at the other end, where in fact they're very clearly elastic solids up to a very large stress, right? So there's a wide range of amorphous solids that you can think of, and going beyond, you have all these kind of examples by analogy. Okay. Okay. So when we talk about mechanical behavior, what one normally talks about, in fact, that first picture from a textbook, probably is illustrating behavior of crystalline solids, right? And in crystalline solids, we heard a little bit on Monday, you have sort of some kind of a picture of what's happening, because plasticity in crystalline solids arises through motions like this, which is basically can be thought of as the motion of this particular defect, which is a dislocation defect. And these are things that not only can you describe them simply. Is this playing? It's supposed to be a movie, but you can image them in the lab, right? And you can see them moving. So they have a great deal of concreteness and reality to them. Yeah. So you can say, at least I know where to begin if I want to talk about plasticity in crystalline solids. By contrast, and that's really why I waste those precious minutes talking about crystalline solids, which is not the topic of my discussion. In contrast, if you look at amorphous solids, you do not have regular translational order, and correspondingly no equivalent of dislocation defects. Deformation mechanisms involve localized rearrangements. This is sort of an empirical observation, and possibly, and this is sort of not very, it's not sorted out to everybody's satisfaction, avalanches of correlated deformation events. So what these localized rearrangements was illustrated in this cartoon here. These are just highlighted atoms, so I'm applying some shear strain, and I see that particles are simply sort of moving along, but at some point something happens, some click happens, right? Where, in fact, in this example, though it's not generic, particles actually move. So they recoil, right, from the direction of stress. And so in order to sort of go from here and build a theory that sort of satisfactorily answers all the questions about what happens at yielding, you need a formulation of the problem that takes into account features specific to plasticity in amorphous solids, such as this, and go from there. But going from there means then asking, how do these events come to be? How do they interact with each other? What do they look like as I go towards the yielding point, etc. So this is now the conceptual part of the problem. And of course, as I've already indicated, there are very many practical applications where this is really interesting, and more as like-minded people get into looking and modeling seriously biological matter, that's one domain where these concepts may find ready utility. Okay, so so I'll just say a little bit about how people are thinking about these problems. So one thing that's sort of an established result, that's a reference point, is this work of Eshelby, which sort of looks at what happens when a local transformation so you take an elastic solid and you say that I'm just going to grab onto one small piece of it and I'm going to reorganize it. So you can imagine, and this is sort of what's probably illustrated, I can cut out an ellipsoidal piece and then I sort of reinsert it in the wrong way. Okay, so you've now created a plastic deformation locally by hand, and you can ask what happens to the rest of the system, right? And what was worked out this long ago is that you have then a propagator or a propagation of stress which is long-ranged, and the propagator looks something like this. It decays as a power of the dimensionality, and it has a certain quadrupolar symmetry, which I guess I've indicated here. And this is now, of course, for an idealized problem, but people have gone and looked for this in computer simulations, and this is now a representation of particle displacements in a simulation of an amorphous solid, and this is a corresponding representation of experimental results, right, in a colloidal solid. So the summary of showing that is these are entities that so like the dislocation defects, this is something that you at least you can't really say what they are, but you can say what their consequences are. But you do see them, right? So that's sort of one reference point. Then you can ask, okay, so you have stress that is propagating, right? And so what happens? So what you can imagine happening is, so this is now like a representation of a bubble raft, which I've divided by hand to cells. I can imagine that in one of these cells I have a local rearrangement, but then from what I've sort of discussed, there will be a stress that now propagates over in a long-range fashion to the rest of the system. So then I can imagine that this will have consequences for whether a rearrangement event happens in a faraway cell, right? So this will then give me a way of going about making sort of coming up with a description of localized rearrangement events that in turn can trigger other events farther away in the system, and this can lead to avalanches and yielding, etc. So now since I mentioned avalanches, a couple of words about where people have spent a lot of time looking for them and studying them. So this is one sort of classic problem that has been studied, which is sort of crackling noise in a disordered magnet, right? It's called Barkhausen noise, and so the noise which you can actually hear comes from sort of reorganization of domains through avalanche events, which can be of, whose sizes can be widely distributed. And so that's where the crackling part comes. And I can sort of, this has been modeled through what's called the random field easing model, where I have each spin, I haven't written the full Hamiltonian, but if I look at sort of what is the net effect of the rest of the system on a given spin, it's made up of three components. One is the magnetic field due to its neighbors, and the other is a local magnetic field which is random, okay? And the third is whatever global magnetic field I might be imposing on the entire system, and I imagine that I vary this in time, right? And so there is a clearly identifiable source of disorder in this system, which is HI, and the strength of the disorder I can quantify by looking at the distribution of these HIs and how big they are. So you call it R for random. And so if I look at now the phase diagram of the system in the external field disorder plane, then you have an interesting phase diagram. I'm not going to tell you all the details, but this is now looking at what happens to the system at 0 temperature. And if I have huge disorder, right, then you can imagine that if I keep cranking up the external field, the magnetization keeps going up, but I don't expect anything dramatic to happen, right? At the other end, if I have 0 disorder, which is like a regularizing model, then if I am in the 0 temperature limit, if I crank up the field, there must come a point where the spins will flip globally, right? And so that's that would happen at the point you hit a mechanical instability, right? An instability. So in between, you can ask what happens, and so what people have analyzed is that there is a critical degree of disorder at which the behavior is critical, okay? So, and near that critical disorder, you have, as you approach the critical point, sort of avalanches of all sizes, right? So there is no cutoff to the avalanche size distribution, which has a power law form, and this cutoff basically goes to infinity as you approach that critical point. And so the idea then has been that this criticality somehow influences the behavior of the system over a sufficiently broad regime that I can think of the critical behavior as the characteristic of what happens when I drive a disordered magnet, okay? And this by analogy has been applied to glasses and other amorphous solids. I'll say more about it, but this is just to give you that background. Similarly, another problem that has been looked at a lot is what happens if I drive an interface in a disordered medium where the disorder is quenched. So I imagine that I have just some sort of dirt sticking on a plate, let's say, in a cell, like a Healy-Shaw cell, and I push one fluid into another from one side. And so I have a surface with a certain surface tension, and this interface rather, and this interface can get stuck at these points where the dirt is, right? So those are the pinning sites, and I can ask what happens if I start pushing this fluid at a small driving pressure, and I slowly crank up the pressure, right? And what people find is that if I now look at sort of some mean velocity of the interface as my order parameter, that velocity becomes finite at a critical driving force, and it sort of increases continuously, right? So this also describes the depinning transition as a continuous sort of critical transition, and people do find now avalanche sizes to diverge as you approach it. And here, the avalanche size that you would describe is sort of, if I, at some force, I have an interface in some location, and I increase the force a little bit, and the interface suddenly moves to a new location. So the area that I covered for small increments of the force can be used as a characterization of the avalanche size. And this also diverges. So these are sort of two models that people have had as references in thinking about yielding in amorphous solids. So based on these, you can sort of make a list of questions that you can ask. What is the nature of plastic deformation events in shear amorphous solids? We have some answers already given earlier in terms of Eshelby inclusion, but we don't really know what causes them, right? So this is, and how you might characterize their sizes, etc. The nature of interactions between these localized events that may lead to avalanches, the character of avalanches before yielding and after yielding, and this is sort of a specific question that becomes important. The nature of the yielding transition, is it a sharply defined transition? This is certainly not the answer you get when you talk to material scientists and ask them, so how does where does yielding happen? They'll say, oh, you have the creation of dislocations, and as you apply more stress, there are more and more of them, and gradually this. So there's no notion of a very sharply defined point at which the behavior changes. So is that true here as well? And in fact, you'll see that when you look at glasses at one end, in fact, the behavior is very continuous, right? Okay, and the last point, and this was really the purpose of talking about these other models that people have studied, is how does the transition here compare to other transitions in driven disordered systems, okay? So, right, so this is, let me not go through it. These are points that these are some answers that we do have, yeah, which I've covered already. So what we do is to do computer simulations of deformation of model glasses in search of some of these answers. And let me not go through all of the, I illustrate all of this in detail. So what we do is to have sort of an energy landscape picture, and we say that if I apply affine shear deformations, shear strain, under a certain type of condition, which is called the athermal quasi-static protocol, then the system, so the athermal means that the system is always sitting at a local energy minimum, and quasi-static means that whatever I do to the system, I do very, very slowly, so it's always sitting at a local energy minimum. And under those conditions, the system will make a transition from one minimum to another only if the minimum that you're sitting in becomes unstable, okay? So these points of instability are the points of interest. So the plastic deformations are the movement of particles that take place at these points of instability. And so the limitation of this approach is that if there are interesting kinetic factors that dictate the behavior of your system, those are not taken into account. And there is sort of a very specific example that I can give you, which is if you look at the avalanche statistics in real earthquakes, one doesn't really find behavior that's close to what you may predict by a model that you think is good. And also sort of different situations, the exponents change a bit. And the current understanding is the inertia of your system really matters for the kind of avalanche statistics that you may measure, right? So those kind of effects would be lost in what we're doing, but we can still hope that some essential features of what happens will be retained. And well, most recently, thanks to a friendly or a constructive referee, we have sort of gone beyond this approximation and done simulations at finite rate and finite temperature, and indeed we can see that the behavior doesn't really change. Okay, so this is now a schematic of what you might expect will happen if I take some system which I represent in this abstract fashion, and I'm shearing the system. Eventually it will go to this other state, and if I think of what's happening in the energy landscape, I'm driving the system up the wall till I reach some point which is a limit of stability of that minimum, and then I make a transition to another minimum. And this cartoon is basically a summary of a popular model called the soft glassy rheology model, which I'll mention again. And this you already saw, and it's not playing. No, it is playing. So, okay, let me not show it again. But here is now a slightly ornate cartoon movie of what happens. So one thing that's interesting to note here is that when you have a system with multiple minima, you sort of deform the system back and forth. You naturally develop hysteresis loops. Okay, okay. I think I've said all of this. So if there's any question of what we're doing, this is a summary of the athermal quasi-static procedure. We deform, minimize the energy, we deform again, minimize the energy, and we keep going. So if there's nothing happening, you'll see some elastic branch. If you have restructuring events happening, you see stress jumps and energy jumps, okay? Okay, so people have looked at this. And so here is some old work. Now, if you just look at a liquid and sort of map liquid configurations to local energy minima, you get a temperature-dependent average that looks like this. So at high temperatures, you're basically sampling something that's referred to as the top of the landscape. So these are the worst possible glasses you could make by taking a high temperature liquid and doing an infinitely fast quench. But as you go to lower and lower temperatures, you anneal the system so that even when you do an infinitely fast quench, you're finding energies that are lower and lower, okay? And then if you take, this is what is depicted here, so I sort of anneal the system up to some time, you end up with some local energy minimum down here, and then if I now apply shear deformation, I'm pushing the energy up, okay? And what is found in this many years ago work is that you seem to sort of increase the energies up to this threshold energy that you found, okay? So the flowing glass will have this high energy, yeah? Now, this is, I'm just giving you the background, the sort of, I'll show you our results and say what we can say about this. Yeah, that's what is shown here. So these are the reference lines, which is this line, okay? But this is not exactly correct, but it's correct in some essential way. But then you can say, instead of pushing my system, and this is how we got started on this, instead of pushing my system in one direction, because if you look at this curve here in the energy, right? The initial part, I can say, the energy is not really increasing. I'm just adding a strain component to the energy, right? This is like the, so this increase in the energy, because I'm still sitting in the same energy minimum, but because I'm straining the system, I'm adding an elastic energy. So how do you decouple this elastic increase in the energy from sort of some structural change that leads to increases in the energy? So one thing you can think of doing is you strain the system up to a point, and then you strain back and ask where did you end up with? And this was done again many years ago by Osborne and Lax, and what they found is that it's complicated, right? It's sort of what you end up with depends on what your initial energy was, how far you pushed, etc., etc. But the interesting observation is that there are situations when the energy will decrease, right? And that you can see. These are the purple curves are the ramp up, and the cyan, the yellow curves are when you come back. And you see that, in fact, there are regimes where the energy is actually going down. So our sort of starting point was to say, what happens if I do this again and again and again, right? So that's how we got into doing cyclic deformation, right? Because this is clearly showing that there are interesting annealing effects when you deform. So this is what we do for a model glass, which is called the Cobb-Anderson mixture, and we do this for a whole range of sizes, and the reason for that I'll mention in a minute. And so there is one control parameter here, which is the amplitude of the deformation, and that's the only control parameter. But there is a second important parameter, which is how annealed the glass is that you start with, right? So to sort of understand the effect of that, we basically work with two glass samples, which we treat as our initial configurations. One is an energy minimum structure that is obtained by quenching a high temperature liquid, and the other is what we obtain by quenching a low temperature liquid. These we refer to as poorly annealed and well annealed. Okay, so we're typically looking at stroboscopic configurations at the end of each cycle and measuring properties. And we sort of have as our time variable the total amount of strain that is imposed, which is 4 times the amplitude times the number of cycles, which we call as the accumulated strain. So what happens as we do this over a range of strain amplitudes is illustrated here. So this is now starting with small amplitude, 2%, 4%, 6%, 7% strain, starting with the poorly annealed glass. What you find is that in all cases, the energy cycle to cycle of the glass keeps decreasing, right? And something like that happens also for the well annealed glass, but it's really so small that you can't really say anything. But it's important to have that comparison, because you see that the two energy curves are failing to meet however long you simulate, right? On the other hand, if you go a little bit above, starting from 8% going to 14% strain, if you, even for fairly short runs, you see that you forget initial conditions. You started with a poorly annealed glass, you started with a well annealed glass, you end up in the same place, right? And these energies now, as I increase the straining amplitude, are going up instead of going down, okay? So something changed between this set of amplitudes and this set of amplitudes. And what you also see is the amount of time it takes for me to reach the asymptotic value is increasing, right, in one way. So it's increasing as I increase the strain here, and it's decreasing as I increase the strain here, strain amplitude. And that gives you a non-monotonic curve. And so the system is becoming very sluggish as you approach a critical strain value at which something dramatic happens, okay? So let me not sort of dwell on this, but basically in the two regimes, yeah. Say what?
So in crystals, when you do the shear cycles again and again, you have fatigue, but you always find that those two become less stable when you the more cycles you subject it to, yields faster, right?
Repeat that.
So it's like, if you think of phenomena like metal fatigue or something,
Right.
so there what you're doing is you are subjecting the material to stress, then removing the stress, and then when and what you find is that the material becomes weaker and weaker as you subject it to longer and longer cycles. Like the material fails much more easily.
Right.
But here it becomes stronger, right, in that initial regime.
So even in a crystalline material, it depends on the amplitude of strain, and that's
Sure,
really
same
key.
phenomenon is there.
Yeah. So no, because obviously, if I'm looking here, you know, I'm
But there is a regime below which you will strengthen the material
Yeah.
the more cycles.
exactly. So this is something that, yeah. So so the quick point here is that in the above threshold regime, if you look at particle coordinates from one cycle to the rest, you find that their motion is diffusive, whereas below there is no diffusion. Okay. So you can say that this is a non-equilibrium transition from localized to diffusive states. Okay. The question is, you know, does it help us understand yielding? And to motivate why this may be useful, I show the standard plot that people make in order to talk about yielding, which is a stress-strain plot. And one thing that should be very obvious here is, if I was looking for a precise point at which yielding happens, there's no point I can pick out of this data, right? And it's particularly bad for for poorly annealed glasses, where the stress increases gradually as I increase the strain. For well annealed glasses, there is an overshoot and there's a decrease. And so if you want, one special point you can pick is the peak of this curve. But you know, you probably have good reasons to think that that's not where irreversibility started, right? So can you do better by looking at oscillatory deformation? And this is now the stress strain curves you find when you do oscillatory deformation. And so here, in order to sort of talk about a transition, you say, let me look at the maximum stress that I developed for any given amplitude of strain. And those are those points, right? And you can see that, in fact, there is something like an elastic branch, but there's a very clear point at which a transition happens, and it's a sharply defined point. And the various details about this, but I'm sort of running short of time. So one thing that is related to what you asked is, if I started with this poorly annealed glass, by the time I'm done with my cycling till I reach a steady state, my stresses have gone up to here, right? So you've actually work hardened the glasses, right? But the work hardening is, in fact, also a known phenomenon in crystalline solids, but let me not spend more time on it. But the long and short of it is, we have a way of identifying a sharply defined yielding transition. And
yes. Actually, we have tried to do the same thing, and in the granular system, that we didn't have any sharp peak in the subject. So, but I think that you have some condition to have such sharp peak. So we have a look at that.
With oscillatory shear?
Yeah.
Okay, I would like to pay more attention to that, but here clearly we do see it. For our model of granular matter, which is soft sphere assemblies, we do see a change like this, but it's not, so for the density we've been looking, it's not discontinuous, and this is something we're trying to understand better. Maybe there is some dependence on the distance away from the minimum jamming density, but okay. Okay, so let me skip all this. So this is now the summary of what we said about the annealing behavior. So below yielding, you always anneal better and better as you increase the amplitude of deformation. Above, you don't, But on the other hand, above the transition, you seem to have a quote-unquote ergodic state in the sense that the final properties of the system don't seem to depend on initial conditions, which is not true below the yielding point. So what's the nature of this energy increase is the next question. Now, according to this clock, I have 10 minutes left. How much more time can I take? Because there's sort of a few things I wanted to go over. Can I take 10 minutes more? Is that okay? Vijay? Sure. Now, I'll run through these quickly because there's a little bit of an aside. But before I start talking about shear bands, I wanted to say some interesting things that are associated with this transition. I already mentioned about annealing, and something that we've been looking at quite a bit, which I won't say more than one slide's worth of, is memory effects. As I said, the system with a number of repeated cycles reaches some steady state that recalls memory of what you did to it. The structure of classes changes in interesting ways below and above the yielding transition. They exhibit this property called hyperuniformity, and there's also some interesting changes in entropy, which we try to characterize for this non-equilibrium system. Okay, so here is this sort of signature plot of the memory. I've trained the system at 6% strain, and then I do a read cycle at an increasing amplitude of strain. And what I find, if I look at the mean squared displacement at the end of one reading cycle, is that this mean squared displacement is 0 exactly at the amplitude at which I train the system, but below or above, it is finite. And so this is a read-off which clearly allows me to tell something about the past history of the system, and therefore is a memory, okay? Lots of questions here, which I won't. So hyperuniformity is something that's been studied quite a bit for driven systems, among others. And the basic idea is that if you look at number fluctuations in these structures, they are sub-extensive. So if I look at the structure factor in the limit k going to 0, it vanishes, okay? And if I look at regions of different sizes, and I ask what is the variance in the number of particles I have, instead of going as the normal proportional to n, I'll have this number going, or the number fluctuation, going as proportional to n to some power which is less than 1, okay? Yeah, so this is from other people's work. This is from our work, where this is now as good as it gets. Below the yielding, all these curves are below yielding, and you see that for the largest sizes that we have, we do have a power law which is not changing as I go to lower wave vectors, but when I go past the yielding transition, there is a change that makes these curves go up to finite values. So there is a hyperuniform to normal transition when you go through the yielding transition. Okay, this is another way of representing this using number fluctuations. I think, okay, there is a size of the region cubed. It looks like I should have, yeah, I've multiplied it. And these are density fluctuations. So anyway, if it was flat, it was normal. You see that in the below yield region, it's going down. So that indicates hyperuniformity. And above, by this measure, you see it getting back to normalcy. But in the range that we study, you don't see that flat regime necessarily, okay? But, okay, this is just for kicks. Maybe I shouldn't spend time on it. I was in a conference last week in IIT Bombay, and when I walked in, Rajiv Gavai, who's a particle physicist in TIFR, had the phase diagram on water on the screen. And that had some relevance to the quark Luan phase diagram that they study, and then I didn't want to be left behind, so I wanted to put this detail about the hyperuniformity of the universe as part of my talk, because there is apparently this property that they call super homogeneous, which is something that people worry about. Not understood, whether it's because of inflationary cosmology, etc. But it is a phenomenon of interest. Okay, so here, there's been a lot of interest in looking at the information content of non-equilibrium systems. You heard some of you, Dov Levin's lectures on this, and this is sort of figures from his work with Stefano Martiniani and company. But this approach of computing the information density as a measure of entropy so far doesn't work so well for continuous systems. And while we're trying to understand it, we said, why don't we look at other measures of structure-based entropies, such as the pair correlation entropy, which is sort of a standard quantity that you study in liquid state theory. And indeed, that entropy does seem to capture quite crisply the fact that you're undergoing a transition at the yielding point. I won't say more. In terms of what is other things that are changing at the yielding transition, one thing I promised was to tell you a little bit about avalanche distributions. And the basic observation here, ignore this is too small. The point is 2,000 particles is too small to tell anything. You have to go to much larger system sizes. And there you see a clear decomposition of the avalanche distributions into finite versus system spanning, okay? So the cutoff here is really determined only by the system size, and you can see that by sort of doing some transformations of variables and multiplying by that power law. And basically, this is now the distribution below yielding, whereas the distribution above yielding is a power law, which would translate in this representation to a flat line, except for the system size cutoff, okay? So what we say is avalanches are finite, or order 1 below yielding, but they're system spanning above yielding, and this happens in a discontinuous fashion. And then you can ask, but are other people crazy to think that there are large size avalanches? And the answer is not really. But there are things that happen in the cycles in which you train the system, right? And these basically anneal out various reorganizations that can take place, which people would see, for example, if they simply did uniform shear. And this is now the size of the energy drops plotted against accumulated strain, the number of cycles, roughly speaking. And what you see is that these sizes get bigger and bigger as you increase the amplitude of deformation, and they last longer and longer, okay? So there's a lot of restructuring that takes place in the process of training the system. Yeah. Yeah.
Somehow understand this by thinking that at large strains there is more internal energy stored in the configuration that I'm basically anticipating as I'm driving the system.
Why don't we come back to these questions at the end? Let me just run through and just finish what I have to say. So something that has been subsequently seen is that instead of doing oscillatory deformation to anneal the glasses, if you simply find some way of producing more and more annealed glasses, and then you do uniform shear deformation to look at the yielding behavior, you do find that in fact the transition becomes sharper and sharper as you go to the more and more annealed glasses. And this has been sort of interpreted as in terms of the random field Ising model phase diagram, where you say that the annealing is tuning the randomness in the system, and so you're going from a discontinuous at high annealing to something continuous at low annealing. There is an important caveat to this, which is if I take a poorly annealed glass, if I do just uniform shear, there is annealing that takes place even in that case, which I have to take into account, okay? But before, I'll come to this point in a minute. So here is what we find in terms of shear banding. You basically find above the yielding strain that displacements from cycle to cycle of particles becomes localized in some region of space, and that's what is shown in red here. And this is just a fun set of movies to show that this is happening. What you're supposed to pay attention to is the boxes. All the red guys are eventually going to yield, and these low amplitudes simulations you don't see yielding, and therefore no shear banding, but I won't wait for that. One thing important to note is the location of the shear band as measured by the displacement of particles is correlated with the energy of the system in that band, and but this is the best part. And so there are very sort of other interesting features. One is the shear bands actually move around in the course of your simulation, and something that's sort of unexpected, at least by me, was that if you look at the density of the system inside and outside the shear band, there's a bifurcation. So the density of the material becomes smaller and smaller inside the shear band as time goes on. The energy of the system, on the other hand, is also a bit of a surprise. Not surprisingly, inside the shear band, the energy goes up, right? But the sine curve is the overall energy, I believe, yes? Yeah, and so that's going down, and of course, inside the shear band, you expect it to go up, but what wasn't really expected is that the energy keeps going down elsewhere in the system. So in other words, even when I have shear banding and yielding, if I look at the state of the material outside the shear band, that energy keeps decreasing. So there is sort of a very clear bifurcation of behavior. And this is illustrated here again. These are the energies that I showed earlier below the yielding point. Now, this is the total energy of the system above the yielding point. One thing that I didn't have earlier is a clear characterization of the discontinuous change, which we do now. If you look outside the shear band, these energies maybe in a different fashion, but they keep going down. And in the shear band, you go to energies that are at the top of the landscape, as I mentioned, the worst possible energies. These are actually even worse a little bit because the density of the material has changed, so that one has to factor. This is something very interesting. I take a system which is shear banded, and I decrease the amplitude of cyclic loading, and what you find is that the shear bands actually anneal out, okay? So, even in these systems where there's a lot of history dependence and so on, there seems to be sort of a fairly unique state that the system will go to under cyclic deformation, which is interesting. Okay, so let me skip all of these, which are not so interesting. This is just, this is something that we did in response to the previous helpful referee comments, which is to look at finite shear rates and temperatures. And the basic point, without going into details, is that the picture basically doesn't change. We have a discontinuous shear banding yielding transition. Okay, so annealing effects are important, and there's been sort of some work by various people listed here, Susan Fielding and co-workers using the SGR soft class rheology model, Kirsten Martens and et al. Looking at elastoplastic models, and Karin Daman, who sort of has an analytic theory for avalanches and yielding. In all these cases, in some sense, people have discussed the possibility of annealing as being important. There's also a fairly large rheological literature where shear banding has been discussed, but confusingly, what is meant by shear banding in that context is very different from what we are talking about. So we are sort of trying to work through this literature to say, okay, what can we say that's new, that will add to the understanding of this. But in the meantime, you can ask, okay, so maybe annealing is important when you do this cyclic deformation, but why should I care if all I'm interested in is driving the system towards yielding by just a uniform deformation? And the answer is shown here. This is now the poorly annealed glass, and this is what happens to the energy as I shear it forward, right? So if you just focus on this curve, and you see that this system, even under uniform shear, clearly is annealing, right? It's going to lower and lower energies, but then you can also sort of try to factor in what I said earlier, which is that the energies that I'm seeing here are the energy of the unstrained system plus elastic energy, right? So I can sort of make an effort to project back to zero strain and look at those energies, and that's what you see here. These systems under uniform shear clearly anneal, right? Less obvious for the low energy, the well annealed case, but this is what's relevant for these analogies with the random field easing model critical point scenario, where even though the authors may not say it explicitly, you assume that disorder is quenched and fixed, and that's not really true. Okay, so okay. Like I said, there is some work that we can sort of take advantage of, but we're in the process of trying to figure out how to put annealing into the picture and to sort of figure out what we can say because of the detailed information that we have through these atomistic simulations about the nature of yielding. Okay, so let me stop there. Thank you for your attention. Sorry for going over time. All questions? Yeah.
So in shear banding, in say nematogenic fluids and all, so you have inside the shear band and outside the shear band, there is a change in like configuration of polymeric material. Outside the shear band, they are kind of like clumped and they are elongated. So in my mind, like inside and outside the shear band, there should be some mechanical difference in the system. In your case, probably it is the density.
The density, the energy, and I could look at 10 other things and they'll all be different. But in the example that you gave, and this is where we are confused a little bit, because a lot of the thinking about shear banding seems to have been very dynamical in nature. So the elongated state is not a possible equilibrium state under other conditions, right? It's really a rheological, it's a steady state condition, right, for the polymers inside. So here, in principle, we can still be thinking in terms of inherent structures at high energy, high temperatures and low temperatures, etc. It's not clear if that's completely satisfactory, but because you're doing this procedure of athermal shearing, you really don't have dynamical effects, right? And as I showed through these finite shear rate simulations, as far as the formation of shear bands, where it forms, etc., finite rates don't seem to matter. Okay, whether it, but all people seem to sort of think about competition of timescales, etc., to try and explain shear banding in flow. But in our case, if we were to translate our results into what might happen, if you were to sort of enter deeper into the flowing regime, we would say that the shear bands will spread. Okay, so steady shear bands, as people discuss in the context of rheology, we don't have. Yeah. So, you still remember?
Well, yeah, but let's just keep that offline. It's kind of tautology.
Okay.
But coming to the shear bands, so the fact that the density inside the shear band is lower, it's quite lower, and it's higher outside the shear band. It's just sort of, if I do a zeroth order kind of cartoon, it's as if your amorphous solids really consists of two types of solid. The high density part is basically has now different mechanical properties, and you're really, you're basically now shearing the low density part between two hard rocks, maybe in a way. I'm exaggerating. And somehow, at the the yielding trend point that we have is assumed at a certain density at the way it is. But this has bifurcated into a sort of, two type of solids that are coexisting now,
True.
Is this a useful way of thinking about this?
It may be, but it's not very clear because.
I don't understand why this is happening.
No, but but the textbook example where something like this would happen is spinodal decomposition. Yeah. But there you have a conserved order parameter, and that's sort of really instrumental. It's not necessary, but it plays a role in creating these heterogeneous structures. But how to think about an analogy here, we have to work through.
Let me confirm the terminology of annealing.
Mm-hmm.
You said that annealing is the process of the cyclic stream. If you add the large number of cycles, that is called annealing process.
No, that's cyclic deformation. What happens is annealing in a certain regime.
Please clarify the annealing.
So what I mean by annealing is something very simple-minded, which is that the glass is going to lower and lower energy states. So if you were doing a cooling experiment, if you anneal, you go to a lower temperature glass, which will have a lower energy.
In a usual textbook statement, that annealing is a slow cooling. Slow limit of the cooling process.
Yeah, but slow cooling.
It is impossible to use such process in the computer simulation. So you have to use some similar process.
No, so when you say you anneal the system, what you mean by it is that you take it to more energetically optimized structures. That applies in the conventional use of the term annealing, and it also applies here. So that's what we mean. Okay. If there are no more questions, you have more questions. Yeah. Okay, one more question.
Actually, this stress and strain curve you showed for crystalline amorphous material, and before the yielding point, it is reversible. So in all cases, I found the stress versus strain curve is linear below the Is it a necessary condition, or you can still have non-linearity, but still?
So in amorphous solids, certainly in the athermal limit, you will have plastic rearrangements at all strain values. So whatever linearity you might see is at best an average property.
Based on some experimental data, actually, I see
That
like
shows,
it's
yeah,
very reversible, but it's not a linear.
Yeah. Ah,
So it's
that's interesting.
but it is not average.
Okay. All right. Thank you very much. Break.